Now let's look at an example where we use a thermochemical equation and calorimetry data to write an overall balanced thermochemical equation for a specific chemical reaction. And we talk about connecting calorimetry data to delta H of reaction, but this time we're going to add one more wrinkle and do it in a limiting reactant context. In our last example, we had stoichiometric amounts of the two reactants. So the big idea was that we could connect the heat flow that we observed in a calorimetry experiment to the delta H for the reaction and generate a thermochemical equation by figuring out how many moles of our reactant we started with. Last time we had stoichiometric amounts of the two reactants. This time we're going to be given masses for two reactants in a chemical equation. We're going to have to decide which reactant is limiting and then base the amount of heat released by the reaction off of the mass and number of moles of the limiting reactant, not the reactant in excess. So the example we're going to deal with is a very dramatic and very fun chemical reaction to witness. This may be one that you've seen in a previous chemistry class, either in high school or in your first term of general chemistry. And this is what's commonly known as the gummy bear sacrifice. If you've never seen it before, I've linked a YouTube video. Ordinarily, we do this demonstration in class in person today, but we'll have to make do with a video for now. So check out this video if you haven't seen this reaction before. It's well worth a few minutes of your time because it's a lot of fun. It's a very bright, obviously exothermic chemical reaction. All right, but for our purposes, this is the setup we're given. A gummy bear contains 2.67 grams of sucrose, which has a chemical formula C12H22O11. When the gummy bears react with 7.19 grams of potassium chlorate in the liquid phase, or in the aqueous phase, KClO3, 43.7 kilojoules of heat are produced. We would like to write a thermochemical equation for the reaction of 1 mole of sucrose. So we're given the balanced chemical equation to describe this reaction, which says that 1 mole of sucrose reacts with 8 moles of potassium chlorate to give us 12 moles of carbon dioxide, 11 moles of water, and 8 moles of potassium chloride. This reaction is exothermic and it releases a lot of heat, which is indicated because we're told that 43.7 kilojoules of heat are produced. Describing heat as produced or released in the text of a problem is a very good indication that your chemical reaction is exothermic and should generate a lot of heat as it goes on. So we have the balanced chemical equation, but when it asks us to write a thermochemical equation, what it's really asking us to come up with is the delta H in kilojoules that goes along with the reaction as written. And once again, what we've been given is some calorimetry data. Someone did this experiment by combusting 2.6 grams of sucrose and 7.19 grams of potassium in a calorimeter and found that that amount of reactants generated 43.7 kilojoules of heat. Now remember, when we have calorimetry data and we want to connect it to the delta H reaction, the delta H reaction is equal to the heat flow divided by the number of moles of your reactant. This time we have to ask, well, which reactant? Because we have two of them and we have a known amount of each. Well, unless you're told that your reactants are present in stoichiometric amounts, you have to assume to correctly determine delta H reaction, you have to divide the heat released or absorbed by the moles of the limiting reactant. So unlike our previous example, this time we need to use the amount of each reactant given to identify the limiting reactant. And so if it's been a little while since you've done a limiting reactant calculation, go back in your book, review limiting reactant versus reactant in excess, and think about some of the calculations you've done before to identify a limiting reactant. What we are going to do is we are going to use the amount of each reactant given to identify the limiting reactant, and then we are going to divide the heat flow that was observed in the calorimetry experiment by the moles of the limiting reactant to determine delta H reaction. To figure out which reactant is limiting, the first thing that we have to do is find the molecular weight for each compound. The molecular weight of sucrose, C12H22O11, is 342.3 grams per mole. The molar mass of potassium chlorate, KClO3, is 122.5 grams per mole. Our first step in figuring out which of these reactants is limiting is to divide the mass of each by the molar mass to determine how many moles of each compound we started the chemical reaction with. So the moles of sucrose, which I'll abbreviate as lowercase n followed by the chemical formula for sucrose, is calculated as 2.67 grams of sucrose divided by the molar mass. 2.67 divided by 342.3, we began the reaction with 0.00780 moles of sucrose. If we do the same for potassium chlorate, we take the 7.19 grams of potassium chlorate, divide by 122.5 grams of potassium chlorate, and that gives us 0.0587 moles of potassium chlorate present at the start of the reaction. Now, the key thing here is in the balanced chemical equation, we need 8 moles of potassium chlorate to completely react with 1 mole of sucrose. So we have to have 8 times as many moles of potassium chlorate as we do moles of sucrose to achieve a stoichiometric amount. I'm going to divide the number of moles of potassium chlorate by the number of moles of sucrose, and I find that we have 7.52, nearly 7.53 moles of potassium chlorate for every mole of sucrose. So what that means is the potassium chlorate is the limiting reactant because we don't have quite 8 moles of potassium chlorate for every mole of sucrose. And therefore, when we calculate delta H reaction, our number of moles in the denominator is going to be the moles of potassium chlorate, not the moles of sucrose. So we would need 8 moles of potassium chlorate to consume 1 mole of sucrose, but we only have 7.52 moles of potassium chlorate in this setup for every mole of sucrose. Therefore, when we calculate delta H reaction as the heat flow divided by the moles of limiting reactant, we have the heat flow Q, which is negative, watch the sign there because heat's being released, 43.7 kilojoules divided by 0.0587 moles of potassium chlorate, giving us a delta H reaction of negative 744.5 kilojoules for the reaction as written. 3 significant figures looks reasonable here because all our mass measurements and our energy transferred measurement are to 3 sig figs. So we would call the enthalpy of reaction here negative 745 kilojoules. It's an exothermic reaction. And we should add delta H reaction equals negative 745 kilojoules to the balanced chemical equation to give our balanced thermochemical equation.